In this video, we'll be mingling the concepts of pre-calculus with the concepts of calculus. The particular example we're looking at is this function, and we want to identify the domain, all of the holes, the vertical asymptotes, the horizontal asymptotes, and the range. The only additional piece to this than you might have done in pre-calculus is that you must provide the limit justification for all that's necessary, and then you have to sketch the graph. So, the first thing I'm going to do is I'm going to go through all the rehashing of pre-calculus material we should know. Number one, we need to start with the domain. To find the domain, we're going to take this function, we're going to go ahead and factor everything we can. I'm not going to cancel anything out, however, okay? What I'm going to do instead of canceling is I'm going to go ahead and just immediately set the bottom equal to 0. That means I'm going to have x minus 4 times x plus 4 equal to 0. And my domain are the values where this can't happen. So really I want to put a slash through this equal sign. That means x is going to be equal to 4, or more appropriately, x is not equal to 4, nor is x equal to a negative 4. So that's my domain, and again, this is how I find it. I set the bottom equal to 0, and I solve that equation. My next step is to determine the holes in the vertical asymptotes. To find the holes in the vertical asymptotes, again, we can do this using the pre-calculus methods. The pre-calculus method of doing this is to look at the original function, right here, factor everything, and anything that can cancel out, this x minus 4 here and here can cancel out. If I cancel that out, the factor that created that domain issue, so x minus 4 created the domain issue of x equals to 4, that is now going to be considered a hole. So x equals 4 is a location where there exists a hole. We're going to do more to this right here in terms of the limits as x approaches the x value of 4, but what we're going to do is we're going to hold off. This is the pre-calculus information that we're going to start with. For the vertical asymptotes, if we recall, the vertical asymptotes are the function values in terms of the domain that's left over. So the domain has a negative 4 that you can't pick. That domain value is our vertical asymptote. Now, recall again, in this problem we're going to want to use limit justifications to verify this information. What we've done here is we've said, well, mathematically and algebraically this is the pattern that has been true so far. We want to ensure that this is going to be true with the appropriate definition of a vertical asymptote and then eventually of a horizontal asymptote. So I'm going to come back to this vertical asymptote and this whole information. I am now going to move on to horizontal asymptotes. Now again, if we recall from pre-calculus, the way that we did horizontal asymptotes is we'd look to the largest power in the top and the largest power in the denominator. If the power on top was larger, it'd be no horizontal asymptote. If the powers were the same, we would divide their coefficients, but with the power on the bottom being the largest, my horizontal asymptote is assumably y equals 0. Again, I need to verify this. I need to verify this, and I will verify this whole in such a way that I identify not only what the x value is, but what the y value is as well. So now I have all this information, and in previous pre-calculus courses, we'd go ahead and do our best to sketch this graph. We also want to know what the range is. In terms of the range, it's a little bit more difficult to identify without having more information about the graph. So we're going to come back to the range after we've sketched the graph. Now, I need to know what this function is doing as x approaches 4, as x approaches negative 4, and as x goes to positive infinity. So that's what I'm going to do for my justifications. We're going to start with the justification of the vertical asymptote, and then we'll come back to the horizontal asymptote, and then we'll finally do the holes. Okay? So as x approaches negative 4 from the left, that's what we're going to start with on the original function, x minus 4 divided by x minus 4 times x plus 4. This is what I'm going to look at. Now you can, again, in this mentality, the behavior of this function here is actually the exact same as the behavior of this function here near 4. So I don't actually have to do anything special with this. I can simply, instead of looking at this version of the function, I can look at the simplified version, because the behavior of this function is the same as the behavior of this function as long as I don't plug in negative 4. Notice if you try, we get 0 in the denominator. But once I identify that this is going to a constant over 0, I know that this should be equal to some form of positive or negative infinity. Let's come back to this negative 4 from the left. Negative 4 from the left would provide us with a number that's approximately negative 4.1. If I plug in negative 4.1, sorry, from the left, yeah, negative 4.1 plugged into here will give me 1 divided by something going to 0, such that this something going to 0 is negative. So I know on the top I'm going to have a positive number. On the bottom, yes, it's going to 0, but before it gets 0, it's going to actually be a negative number. So when I have a positive divided by something going to 0 that happens to be negative, this infinite limit is going to a negative infinity. This verifies first and foremost that x equals negative 4 is a vertical asymptote. I have checked that this is a vertical asymptote. I need to check the other side, however, to ensure that I know what the limit is doing. Now I'm going to go ahead and avoid writing all that extra stuff. I'm going to simply write down the simplified function. The limit as x goes to negative 4 from the right side is going to do something exactly the same. Constant over 0. But this time on top it's going to go to a positive number, and on the bottom, if I'm plugging in, say, negative 3.9, coming in from the right side, negative 3.9. Negative 3.9 plugged in for x here gives me a positive 0.1. So then my bottom value is positive. Now I have a positive divided by something going to a positive. This is going to give me a positive infinity. Again, this second checks the vertical asymptote. Every single vertical asymptote that we evaluate must be evaluated from both the left side and the right side at that x value. Next thing we can do is we can go ahead and check the holes. In terms of the holes, to verify those, we simply take the limit as x goes to the value of x, in this case 4, of the original function. And again, that original function, this one right here, behaves exactly the same as this one does everywhere except for the value of negative 4. So I'm going to go ahead and just use the simplified version of the function. Can I plug in the value of 4? And the answer is yes. If I plug in the value of 4, I get 1 over 8. So I know that x equals 4, there is going to be a hole at the graph. More importantly, I know if x equals 4, comma, my y should be equal to 1 over 8. And when I say equals to, I'm going to go ahead and put a slash through that. Is not equal to 1 over 8. It's approaching 1 over 8. So I know more or less where the empty hole is going to perfectly sit on this graph. The last thing we have to verify is the horizontal asymptotes. To verify the horizontal asymptotes, recall you simply take the limit as x goes to positive infinity and the limit as x goes to negative infinity of the original function. This original function being x minus 4 divided by x squared minus 16. I do this way because it's going to be the exact same mathematical setup. The largest power of x in the denominator is 1 over x squared. I'm going to multiply top and bottom by that. You'll notice on top we'll end up with 1 over x minus 4 over x squared divided by 1 minus 16 over x squared, making sure that I still have that limit sitting in there because I didn't evaluate that yet. As x goes to infinity, the top is 0 minus 0 divided by 1 minus 0, which is 0 over 1, and mathematically acceptable. If the bottom was 0 as well, 0 over 0 would not be something we're allowed to write. But this right here is 0. And therefore, if the infinite limit approaches 0, it tells me that my horizontal asymptote is y equals 0. And that verifies it from one side. Over here, I'm going to do the exact same thing with the negative infinite limit. Recall that the only time that the negative infinite limit is anything different than the positive is when there's a radical in there and we're multiplying by an odd power of x. So I'm going to go ahead and basically do the exact same thing I did in the positive infinite limit. All the math ends up being the same, such that this top piece goes to 1 over x, the second top piece goes to 4 over x squared, and then the bottom pieces are 1 and 16 over x squared. As x goes to a negative infinity, sure, this approaches a negative number, but it is still approaching 0. And therefore I get 0 minus 0 divided by 1 minus 0, giving me the value of, once again, 0 overall. That checks the horizontal asymptote from the other side without any issues. So, given that I've identified the domain, the holes, the vertical asymptotes, the horizontal asymptotes, I should be able to sketch this graph. I'm going to do it right here. I know at negative 4 I have a vertical asymptote. 1, 2, 3, 4. There is a dotted line. I know at the y equals 0 there's another horizontal, or a horizontal asymptote. I'm going to draw that dotted line. As we approach negative 4 from the left, I'm going down to negative infinity. So now I can identify that that's happening. As we approach negative 4 from the right, I know it's going up, so I can identify that that's happening. I know that as we get closer and closer to the value of 4, we should be getting closer and closer to the value of 1/8. So if this value right here is 1, I go 1, 2, 3, 4. 1/8 should be somewhere right about there. And again, I'm drawing an open circle there because that's a hole. So now I've identified my vertical asymptote on the graph. I've identified my horizontal asymptote on the graph. I've identified the hole and where it exists. And I know that this function has to come down, and as I get closer and closer to the value of 0, it should approach that asymptote. Same thing from this side. As I get closer and closer to the value of a y equals 0, positive infinity or negative infinity, it should approach the y value of 0. One thing I should probably identify is what is the x-intercept and what is the y-intercept. Again, to recall what the x-intercepts are, I'm going to go ahead and have to set the equation equal to 0. There is none. If I want to find the y-intercept, I plug in 0 and I get 1/4. So technically this is not one I want it to pass through around at this point here. Okay, so what we should do to graph these functions is not only find the domain, the holes, the vertical asymptotes, the horizontal asymptotes, the range we can look at the graph, but we should probably find the x-intercepts and the y-intercepts. In this case there is none because it doesn't cross the x-axis. And for the y-intercept, again, recall you're just plugging x equals 0 in. When I plug x equals 0 into the original function, I get an x of 0 and a y value of 1/4. So that's what that point is right there. And the range based on this information is all values from negative infinity to positive infinity except 0. So I'm going to go up to 0, put an open circle, go from 0 to positive infinity. And again, right here, you'll notice that there could be a break in this graph at x equals 4. So the range at that location should also be removed. So from 0 technically to 1/8, and then from 1/8 to infinity, because again there's a hole at this location, so that y value is not actually being obtained. That completes this problem. It's not a short problem. You have to make sure that you show all those limit justifications, but 80% of the work that we do, domain, holes, vertical asymptotes, horizontal asymptotes, and range, are pre-calculus concepts, as is the graph. All of these limit rules are simply just justifications to verify that our math is correct.